Okay, the homework was try it yourself. Questions at the back. How'd you go with everything? Okay, I mean, the last few questions at the back. Have you guys tried the inkjet question?
Yes.
The inkjet printer question? That was, I remember that in 2020 or 21, it was exact same format. In James Roos, they actually had that in their assessment. I mean, like they're giving the formulas and they used the scientific skills. And that's not quite a part of the syllabus. In syllabus, we never teach you like exact printers too. It was pretty tricky. I would have picked like that's one of the hardest questions they can get in chapter 1. And I'll try. What I do is I'll give you like a prints of the past HSC questions up to 2022. 23. We're gonna go through the papers of the whole. So let's do some module chapter 1 question, and there are quite a lot of the chapter 1 in HSC. So let's start. Try yourself. So this is page 16. Did we do 16 question 1 together last time? So let's move on to question 2 then. Did we do that too? No. Okay, we're gonna start from that too. All right. Electrons from the hot filaments are emitted into the space between the two parallel plates, and they are accelerated across the space between them. So what you have to see there is, if this is known as electron gun, and you will see it quite a lot in the comment in module 6 and also in the module 8 when we're discussing about cathode ray experiment or J.J. Thomson's experiment. I hope you have heard about that too. If not, it doesn't really matter. You have two sets of the DC connected. One is 6 volts, another one is 100 volts, which means you need to know that the purpose of each of the voltage that you're connected to. This is connected to producing, or sorry, I should say emitting the electron part there too. This 100 volt sign is in the purpose of the building up the electric field. So you have to understand the situation there. Oh, we have a side that's emitting the electrons in the 6 volts, and 100 volts is connected to 2 parallel plates, therefore producing what? That electron, the electric field with positive and negative plates too. Remember that the longer side means positive in a DC, so this means that this plate is now positively charged. This side will be negatively charged. And if you can think about what happened here, if the 6 volts is connected to the negative charge, it's emitting the electrons. The electrons getting charged or polarizing the one negatively charged plate. Because we have a positively charged plate adjacent, means electron will now start to move towards the side over there too. So A, which battery supplies the field to accelerate the electrons? So it's accelerate the electrons. So what happened is this is 100 volts is accelerating. Remember that acceleration is change in the velocity. It's getting make electron move faster. So 100 volts is accelerating electrons due to the electric field generated. Again, electric field strength is not an acceleration. I hope you remember that. We're going to use this anyways. F equals to QE, that is equals to MA. If you're looking for the acceleration, but you don't have to show that, but you can just write it down. If you want to get the acceleration, the electron applied, A would be then QE divided by M, where Q is the charge of the electron, E is the electric field strength, and E is known as V on D. Okay? B, how much energy would be gained by electrons in crossing the space between the plate? Do you remember that the voltage voltage in electric field or any of like in a DC batteries is always confounded by the energy differences between the two divided by the charge, which means it's either be W on Q, which is the same as delta K on Q, or sometimes known as delta U on Q. Yep, so question's asking you, hey, how much energy would be the gain? That means we need to find the delta K, same as work done, which is, energy gain is same as the energy differences basically. Does it make sense? Like a bit of like literal meaning, then it's simply Q times V, that is minus 1.602 times 10 to the power minus 19. That's a charge of an electron times that 6-fold. Not the 100, it'll be 6-fold. Because that will be the energy from this side over here. Then, therefore, we can find that 6.2 times 10 to the power minus 19. That times that 6 simply. You're to get 9.612 times 10 to the power minus 19 joules. Just leave that in the exact values because we are not given any significance here yet. See, how would you answer to B change if the plate separation was halved? We're not really given the separation here, so we don't really know. The 100 volts is gained and energy will be gained. So consider here as the electric field is defined as V on D. Okay, that is the 100 volts divided by the separation of the plate. That's given. Okay, that means that this will do something about the energy. So let's think about the relation here. When the E is increased, the acceleration is getting increased. What are the consequences of the increase in acceleration? So let's see that here. As means E is directly proportional to A. That means increasing in E would increase the A. Again, think about the mechanics. Increasing the acceleration means that it will make the electron move faster, or like changing the velocity more faster too. Means that increase in the final velocity. Does it make sense to all? Okay, so increasing A and that too means as the K, which is the kinetic energy, is found by how? Half mv squared, means that leading that K would also get increased too. Does it make sense to all? Okay, I'm just showing you some mathematical, like some kind of relationship here. So this is why you need to use the understand the mechanics. So where do we get the E from? This is not an energy, by the way. There's an electric field strength, which is defined by E equals to V on D, or E equals to V on D on the top too. The separation is halved, then what happened to the E? What happened to the E when we decrease that to the half? It'll be increased by 2, increased to the 2E. Okay, or you can show that like I showed the mathematical approach of that too. When E is equals to V on D, when the D is replaced to the half D, this would give E1 equals that. Then the simple E2 would be V on 2, half of the D. This gives you 2 times 2 V on D. That is 2 times the initial electric field too. It's good kind of approach they can use. You may get you will get actually one questions about ratios as we did in module 5. Remember that, like a capitalist flow, increase in the R, decrease in R. How does that affect the time period and stuff like the questions too? I mean, the similar things in module 6. That's the answer. It means that as the electric field is getting increased by 2, then we got to follow the consequences. That increase in the electric field would increase the acceleration inside of the electric field, therefore increase the final velocity, which makes the greater kinetic energy. So the kinetic energy will be actually when the V is increased by 2, then you would expect that kinetic energy will increase by 4 as a V square. Does it make sense? Okay, so that's a bit of like a mathematics approach they can use. All right, let's move on to D. How would you answer to B change if the terminator of the 6 battery were reversed? Okay, when we get a reverse of the 6 volts, think about what happened. Means that this now showing the electrons getting charged, but when we reverse the 6 volts over there, it's actually electrons moving in the opposite direction. Okay, but doesn't really matter like where the electrons goes into, because as long as we charge that to the negative over here, okay, doesn't really matter electrons moving into this or that direction, because it will reaching to the destination of the negatively charged plate. Get started like charging that negative charged plate too. What I mean is, it doesn't matter if you're going like upward and downwards. Eventually, electrons will reach to the plate of the negatively charged. Does it make sense to all? Steph, you okay? Okay. Because that negative charge coming in for 100 volts. Exactly. So what happened here is, as soon as electrons reaching to that plate over here, we're kind of pushing the electrons go into that. So 6 volt is something that is pushing electrons move to the negative charge plate. But you see the consequences. As we're pushing that negative charge, it is keep pushing like a waterfall, you can imagine. Because we have a really strong positive there, you're gonna fire it. You're gonna fire it. So you're gonna push that and fire that, like we're giving really high pressure of that water. So that's basically similar to building up the high pressurized water pump, the pressuring. Okay, so for D, it doesn't really change. It doesn't really affect any of those the charges or the energies. But E, how would you answer to B change if the terminal of the 100 volts battery is reversed? Now this is something that we have to think about in here. What that meant is, instead of having the negative charge plate, we now started having the positive, because we reversed that to this, make it longer. Then electrons, think about it here, coming out from this side over here, will love to stay on the positively charged terminals. Will it ever go to the negative charge terminal then too? No. So this means that there will be no electron flows inside the electric field. Simple as that, because the positively charged plates now get attracted all the electrons, kind of captured it, or kind of make them stays into that positively charged plate, so there won't be no electron flows expected. F, how the size of the electric field between the plate and thus electric force of the electron changes if the plate separation was halved. I kind of talked about that over here, so it's kind of a repeating question. Sorry about that too. Okay, but that's basically increasing the when the half separation is halved, electric fields getting doubled. Therefore, or you can consider over here. From this, I showed them. Let's kind of finish up. The A is known to be QE over M. So A is now get double to A, because we have QE over M, where A and the E is increased by 2. A must be increased by 2 as well too. Okay, this will affect the K more likely increased by 2, therefore, or like increase the kinetic energy too. You don't have to really find the quantitative, just explain that what happened as a consequences. G, explain how your answers to C and F are connected. C and F. So C, what we had is how the answer changed, the separation was halved, and that too. So pretty much the same. Okay, let's move on to the next questions. It's more calculation involved questions then. Calculate the acceleration of an electron in a uniform electric field of strength of the 1 times 10 to the power of 6 newtons per coulomb. Please remember that I've been repeating this many times. Electric field strength is not an acceleration. To find that, F equals to QE equals to MA again, then A is equals to QE over M. Okay, Q of the electron is minus 1.602 times 10 to the power minus 19 times that given electric field, 1 times 10 to the power minus 60, so power of 6. Mass of the electron that will be given in your formula sheet. So 9.109 times 10 to the power 31. So all of those answers will be given, so you don't really need to worry about. But if you can memorize the this charge of the electron, it will save you time to write your answer. Okay, so that times 10 to the power of 6 and divided by 9.109 and 10 to the power minus 31, then you'll get the 1.757 times 10 to the power of 17 meters per second. Now, it would have a negative, by the way. Yes, acceleration can be negative because it determines the direction. So what does it mean by negative in acceleration? It means that 17 there, it will in meters per second squared to opposite, at opposite to the electric field direction. So having the electric field, that positive, negative, you know, the electric field flows from, remember the electric field is from the positive to negative going downwards in this case, but electrons will go against because it will move towards 2, electrons will move against. So that's what they mean from like, the negative, the symbol of the acceleration. It doesn't mean going downwards, guys, but just be careful with that because yes, we explained that gravitational acceleration is going downward, therefore it's always negative. It's a fixed direction downward there. It does not have a fixed direction. It will be relative because we can switch the polarities from positive to going downward now to mean electron will move opposite side, which is going downwards in that case. B, starting from the rest, how long would it take for the speed of the electron to reach the 10% of speed of light? Okay. B, speed of light, that's known as C, that's known as 3.0 times 10 to the power of 8 meters per second. It's good to memorize that because we're going to come back to the C later on to module 7, but for now, so 10% of the C would be simply 3.0 times 10 to the power of 7 meters per second then. Does it make sense? Okay. Asking you that this is your final velocity. So how long would it take? So this is what? You got the final velocity. You got the U started from 0. You got the acceleration. We just found that. I'm going to take just a magnitude in this case because we don't really concern about the direction. Or if you can, because we can find the time as well too. What do we have? We have a V, U, and A. So therefore, we can use V squared equals to U squared plus 2A. That's 2A. Yes, V equals to U plus AT. The motion equations. Again, you're gonna deal that in module 6 as module 5 or even module 1 and 2. So V comes out. Where is a B? This is B. 3.0 times 10 to the power of 7 is equal to 0 plus 1.757 times 10 to the power of 17, that times the T. So simply T is equals to, that divided by that, 3 times 10 to the power of 7, that divided by 1.757 and 10 to the power of 17, you would get 1.707 times 10 to the minus 10 seconds. So that's like what? That's like, you can't even measure that. There's a pico, even greater than picoseconds, so you can't really see it. You can't really measure it with your stopwatch. See, what distance would the electron travel in that time? Distance, okay. What is this? S is equals to UT plus half AT squared, or even the V is equals to U plus 2AS. V squared equals to U squared plus 2AS. You can use any of those, basically. So, like, I'd rather use the second one because this is a tip. Taking the first equation using the T, this may induce some sig-fig error because this is not an exact value, by the way, unless even though they could say save the value in your calculator, it's not the exact values. But if you want to use that, doesn't really matter for that too. So my tip is, if you have a save of data in your calculator, just use that as an answer. So what that means is U, which is given as 0. So S is equals to 0 plus half times acceleration, that's 1.757 times 10 to the power of 17. That times that T squared, which is 1.707 times 10 to the minus 10 square like this. Show they're working out. Okay, if you have some saved up data there, then use your calculator saying, oh, I have this value, 1.707 saved up data, so square that, times that 0.5, which is half, times that 1.757 times 10 to the power of 17. Then you get 0.00256 meter. Okay, or 1 meter, actually, in the 4 sig figs in this case. You're gonna get the very similar answers by using the first equations too, so it doesn't really matter, but it's up to you. D, if the answer to C was actual spacing of the plates producing the electric field, what was the voltage drop or the potential difference across the plate? So if this is like a separation, this is the D. This is what the question is asking, telling you that, or which is a separation between the two plates. Then what if the voltage drop of the potential difference? So don't get afraid of the potential difference too. It's simply asking you to find the voltage. That's it. Okay, as we know, E is equals to V on D, and this is a really easy question once you understand, oh, potential difference, voltage. Then V is equals to E times D. That is, E value is given 1.0 times 10 to the power of 6. That times that given value, 0.02561 in the meters. That times that 1, 10 to the power of 6. Then you'd get 2561 volts. In the 4-6 in 3-6 figure with 2560 voltage. It's quite a high voltage compared to what we actually use in everyday life. 4. Now this is it. This is the question. In an inkjet printer, small drops of the ink are given and the control charge and the phi between the two charge plates. The electric field deflects each drop and thus controls where the drops lands on the page. Let M of the drop, M be the mass of the drop, Q the charge of the drop, V the speed of the drop, and I horizontal length of the plate crossed by the drop, and E is the electric field strength. Okay? Develop the expression for the deflection of the drop then too. So let's try to understand in like how the inkjet. We don't really use the inkjet printers anymore because we have so many like cheaper laser printers. But that's what we used to do. That we assume that we have. Okay, I show the real thing. Like we have a printer. Let's say we have a printer. Okay, inside of that we have installing some ink in it. Okay, what you see there is there's a paper, A4 paper goes in. So you've seen that on the top of the A4 paper, okay, there is an ink getting ready to dispel. So I should assume we have an ink coming out. This is ink. Okay, so the ink kind of dropped, kind of sprayed or dropped. But on this adjacent, on this side over here, we have an electric field installed that because we have a plate. It's a plate which is connected to, say, DC batteries like this. Okay, which means it makes them to be positively charged and negatively charged in this side over here like that too. Now, when the ink is shooted from the ink cartridge, that this ink is get charged. We make them to be positive or negative. So that's why they're quite expensive in the high technologies. Just imagine it here. What if the ink from the ink cartridge is now positively charged? Then obviously, because of the electric field, it will get attracted towards the negative there. If that's negatively charged, you move towards the positively charged there too. Does it make sense? So it will depend on the strength of the charge that it will decide that the landing point. It may land over here. It can land it over here. Okay, it can land it there and there. Depends on charges. Does it make sense to all? So can you imagine oh, this is something very similar to the projectile motions once you understand the point. That, oh, if I just flip it, if that's confused you because of the vertical, I can redraw that as from the ink is ejected. We have ink charged is ejected. Okay, we have A4 paper here like this. Okay, we have some plates on the top and the bottom, or maybe beneath the paper, like that. All right, then depends on charge, the plus and minus. Let's assume there's a negatively charged. That means it will go up. sorry, A4 should go this direction. Okay, it can land it like a projectile motions in this case. So what I've done is I kind of 90 degrees flip. Okay, this is what mechanically what we have in inkjet printers. This is like I show you like to understand as a projectile motion. Then does it make sense though? Okay, so what we're given here is then you're given a few things. That m, we have m, which is the mass of drop. We also given the q, the charge of the drop. V is the speed of the drop, and I, which is the horizontal length of plate across the drop, and E. So it's not I, it's actually L, given here like that. So L would be horizontal length of the plate across by the drop. So this is the L, basically, from the starting point. That's what they mean by L. Okay, now, if I just give you a question, like without ignoring all the plus and minus of given over here, if I just give you like a projectile motion question, then okay, we may think that as this is the mass of the object we have. Yes, this is a charge of that. But V would it be what? The speed of that initial velocity. We can take it as initial velocity like this. Okay, what would be the L? What would be the L then? What is displacement, horizontal or vertical? The vertical displacement, which is SY. Okay, what about the E, the electric fields? Now, can you you can picture that? Oh, how I'm gonna proceed from here? That I'm gonna deal that as real projectile motion question. That Uy is 0. Okay, and the Vy is unknown. Why? It's the same as that we're dropping something from the clip going downward too. This is the same situation. That and Sy equals to like some Sy is equals to like I just gonna take like some negative, get rid of the L, or it could be positive and negative. So put the L in this case here. You can just say negative if you like to. It doesn't really matter. Does it make sense? Okay. Now in the previous question we found that the relationship between the force of the charged particle in the electric field can be found by QE, which is same as what? MA. Then can we just rearrange that to, oh, that means acceleration must be QE over M like this. So this is what? Is that the horizontal or vertical acceleration in that case? Well, just thinking about this situation here. This is your vertical acceleration, just like a gravity, basically. Remember that I'm kind of solving the projectile motion question using a different setup of the charges. So you're given a situation that Uy is 0 and that. Now let's solve that. Considering that Sy can be found by Uyt plus half Ayt squared like this. Okay, then you get the L or minus L. So if you decided to get the minus, then we have to do the minus of the Ay too. So I just gonna leave that for now. Okay, L is then equals to half times Ay, which is QE over M times the T squared like that. Does it make sense up to here, this point in here? Then you get the formulas that L is therefore QE T squared over 2M. Equation 1. Any questions up to this point? Deflection? Where is that? Deflection? Oh, deflection. Deflection means that in terms of the L. Or hang on, I just gonna go the horizontal length of the plate crossed by the drop. Sorry. Okay. Sorry guys, my bad. This is SX. Yeah, been a while. So let me do it again. We need to find SY. Let's say deflection, D is a deflection. This is what I mean here, deflection. So this is D, that's L. Okay, so that would be deflection. that from the initial point going downwards. So let's do it again. Then the deflection would be then uy as sy equals to uyt plus half ayt squared. We're going to make that now. D is then equals to half times the QE over M times T squared. That D is equals to then QE T squared over 2M. Equation 1 from the vertical. Okay, now from the horizontal then, what we can tell is we have given the speed, initial speed of the, which is the V. The V is the initial speed. Isn't that the same as your ux value, the initial horizontal velocity? Because it is shooted in the V. Imagine about this situation here. It's the exact same question. This is same as what? The Vx. According to the law of the projectile, we learned that there is no horizontal acceleration at all. Then we can bring it here. Sx, which is the range, that is the same as the L. This time is equals to ux times the t, that is vt simply. So let's write it again. L equals to v times the t, then t will be same as L over v, equation 2. As I want to get rid of the t, because we are not given the t as our variables, I can substitute the 2 into 1. Yep, then you'll start to get d is now therefore q times e over 2m times the t square value, which is L over v squared like this. Just rearrange that, or just leave that. Q e L squared divided by 2mv squared. This is the expression of the deflection in terms of the Q, E, L, and M, and V. So if I just give you that formula, guys, okay, just giving you this, so then this is like, hey, this is a deflection. You'll be like, what the hell? What the hell? Where did you get this from? Oh, do we need to memorize it? This is like this is a thought from the James Ross people before too. They were like, oh, should I memorize it? I'm like, no, never memorize that, because this, you have to deal with that as same projectile motion. And this is what I mean by examiners love to give a question mixing the module 5 and 6. It looked like module 6 question, but at the end, when you solve the question mathematically, this is the module 6 question, module 5 question. And this is what I'm expecting to know for the current year 12 to taking HSC 2024, because physics nowadays is getting more mathematical heavy in terms of this expression or deriving expression like that. But does it make sense to you? Okay. Another reason why I focus so much on the projectile motions in module 5. We did so much practice on it too. All right. B. Then with the values of these given, L is 1 centimeters is that, and so sorry, that's not 106. That should be 10 to the power of 6. So typo there. Calculate the charge required on the drops on the to produce deflection of the 1.22 meters. So once you get that expression, this is just simply a substitution question. This is so easy question then. Okay, but without A, you can't do B. So let's write it down again. The D deflection is known as now QE L squared over 2mv squared like that. Everyone good up to this stage? I'm just copying that down. So you're given that. You're asked to find the charge required. So let's rearrange the in subject to the Q. Q is then equals to 2mv squared D over E over L squared like that. So substituting all that, 2 times mass is given 10 times 10 to the power minus 10 times the velocity is 20 meters per second. Deflection is given a 1.22 millimeters. So make sure you convert it into the standard unit of the meter. That's 1.2 times 10 to the power of the minus 3. That's how you convert it into milli. Okay. 20 squared, is it? Oh, sorry, I missed the 20 squared there. Okay. And E was given as 1.2 times 10 to the power of 6. And then lastly, L, which is 1 centimeter, is known as 0.01 square like that. as 1 centimeter is 0.1 meter. And put that all into the calculator. 2 times 10 times 10 to the power minus 10 times 20 square times 1.2 times 10 to the power minus 3 and divided by 1.2 10 to the power minus 6 and divided by 0.01 square, you'd get 8.0 volts. Sorry, charge. 8 times 8 coulomb.
Wait, so 1.2 millimeter is. Wait, doesn't meter have to convert to centimeter and then millimeter?
It's 1.2 is 0.12 centimeters.
Yeah.
That's 0.0012.
Okay.
Yeah? Yep, because 1 centimeter, centi is basically 10 to the power minus 2. Because from centi to milli, 10 to the minus 1. So milli, the way we can think about milli is always be 10 to the minus 3.
Yeah.
Like liter to milliliters, grams to milligrams, for example. I don't know, unit conversions sometimes trick you that, what's that? What was that again? Yeah. So it's good to let them come back to it. If you're not too sure about unit conversions, yeah, it's a good idea. Like the type of centimeters convert back to 2. So you don't have to write it in 10 to the minus 3, but you can do it your own way as long as you get the same answer. But make sure you put the coulombs for the charge of Q, not the volts. All right. How many do we have more? There are a few. 5. I've got to do some more, and we're going to move on to the HSC questions because we're running out of time. I can't do everything, but I will check your answers. And what I do is I will post up the answers for those and the rest of the questions after we finish question 5 and 6, up to like some 7. 5, an electron traveling east at 1.2, again typo, sorry guys, 10 to the power 5 meters per second enters a region of the uniform magnetic field of the strength 2.4 Tesla. A, calculate the size of the magnetic forces acting on the electrons. Do not get afraid of the word magnetic force. It simply means that the force from the magnetic field to the charge. And I taught you that, that's simply F equals to QVV sine theta. Okay, that's what I mean by the magnetic forces. So what you're given here is you're given the electron, which is minus 1.612, 10 to the power minus 19 times velocity-wise is given 1.2 times 10 to the power 5. Magnetic field strength of 2.4, that's given. So it's going into the traveling east and enters a region of that, which kind of tells you, we just can assume that sine theta is 1, maximizing the amount of the force that too. So it's simply 1.602 times 10 to the power minus 19. That times 1.2 times 10 to the power 5 times 2.4. Then you'd get 4.614 in 4 sig figs. How many sig figs were given? So let's fix that to 2 sig figs. 4.6 times 10 to the minus 14 Newton in 2 sig figs. Easy. Okay. B, describe the path taken by the electron given the reason for your answer. So, in this case here, negative, yeah, it would be direction of that too. So we kind of ignore that because we only consider the size. It's actually given here, size of the magnetic forces. So it means it's simply asking the magnitude. In that case, you can absolute the negative values or just kind of ignore that negative value in terms to calculate the magnitude. Okay, this doesn't really give you. I feel like I'm missing a diagram there. Assume that I give you a situation here. Electrons moving to the east. Okay, assume that this is moving into the field. Magnetic field goes like this. So, if this is east, what would be this direction, guys? If this is east and this is a B, if this represents the direction of the B field, if the right hand side is east, what would be that direction then? You got to think of like a bit of a 3D there, okay? I'm east, north, east. Okay, so that's going in. I'm talking about this direction there. So it won't be like a north and east in this case, okay? It's basically moving backwards or degree into the page. Okay, so that's a little bit of the 3D vector. A 3D vector. I hope you don't get it. I hope you don't get it. So what about I change the direction? Let's make it easy then. North. How about that? So that's moving to north, and this is direction of the SAB. Okay. Now, what do we need to use to determine the direction? FBI, I mean, that's the magnitude, but I'm talking about direction. And remember that electron or charged particle in the B field while experiencing some centripetal force making a circular motions. Does it make sense? Okay. So that, yeah, I ask you, like, don't try to understand the point. Just it is what it is. This is what happened. Yeah. Well, what happens in the electric field? Does it make a circular motions? It's a projectile or to move towards the electric field. So because it won't make the circular motion, it can make a circular at all too. But this is actually making circular motions. So how do we determine the direction? I ask you to use that your right hand. It's either be, it's in the textbook in the syllabus called a right hand palm rule. As I said, like right slap rule. Some people say that too. Or I personally try to like to use FBI gun. Okay, but because of middle fingers, we don't really use that a lot too. But this is probably the best way to you don't forget about it. FBI, that's it. Okay, so what is this? F is telling you the direction of the force can be produced from that. B is direction of the magnetic field. I is direction of the current. So I ask you to remember that the direction of the electron is always be opposite to the direction of the current. This makes sense? Which means if the electrons move into this direction, the direction of the current would be the opposite. So draw that on a separate arrow. So don't confuse that. Oh, we have an E, so my thumb goes to that. No, it should be out of direction like this. Okay. Then what about your middle, your index finger is moving up like this. Does it make sense? Then your middle finger or your palm is facing towards too. So what you started seeing is electron will now make a circular motions from east to north, going into the page and out of the page like this. Okay, so this is what I ask you to. This is kind of like a general, like a rules that you have to use, FBI. And again, we're going to use this again when we describe the motor effect today, telling you how we determine direction. Just use your right hand or left hand palm rule. Yes, out of syllabus. Totally out of syllabus. You can't write that too. But if you just remember that, oh, the thumb is now representing the direction of the negative charge particle, which is the electron. Then FBI said FBI applied. B is going up. A is going that. You show that fingers going into straight away. Okay, this is the trick and the tip that I can give you, and we're going to use the left hand palm rule later on to when we talk about inductions too. So remember that lefty. I don't know. Is anyone lefty here? Okay, no, you can think about, most likely dominant hand, right hand is positive, non-dominant hand is negative. Okay, so quick tip you can think about to determine directions. Let's calculate the magnitude of the acceleration. So again, this is a force, means that we can do this is same as the MA. Does it make sense? Then A will simply becomes 4.64 times force divided by mass of an electron, which is 9.19 times 10 to the minus 31. Okay, that is 10 to the power minus 14 and divided by 9.109 and 10 to the power minus 31. Then you'd get 5.05 times 10 to the power 16 meters per second squared. Now, guys, what would be the direction of this? I mean, it's not really asking the direction, but if I ask you, hey, what's the direction? What's the acceleration in terms of the magnitude and direction? Oh, remember that. Towards the center of the centripetal force, towards the center of the circular motions. Okay, because this is the same as the centripetal force too. But did you notice that? Because you're given FC, you can ask to find the the radius as well too. Okay, food for thought. 6. Let's do up to 6 and move on to some questions if you have any. A. What is the size of the magnetic forces on an electron entering the magnetic field of 250 megatesla? Okay, let's do this. Size of the magnetic force, so electron entering that, so simply using F equals to Q VV sine theta. Saying the entering means we can assume that this is basically going perpendicular to the direction of the magnetic field. So again, typo. Remember, I fixed that. Couldn't do. Electron charge 1.602 times 10 to the power minus 19 times velocity is moving in 5 times 10 to the power 6. It's pretty fast. Millitesla. Milli means 10 to the power 3 again too. So simply don't bother to convert 10 to the power minus 3. That's all you need to do. Okay? You don't have to show 0.24 or 50. You don't really need to. Then QVB 1.602 times 10 to the power minus 19. That times 5 times 10 to the power 6. That times 250 times 10 to the power minus 3. You to get 2. In given significance of 2.0 times 10 to the power minus 13 Newton. This is the amount of force, or the centripetal force. So B is asking you, hey, find the mass of the electron to determine, use the mass of the electron to determine its centripetal acceleration. This is same as what? A, C, because we know that it's making the circular motions. So AC would be simply be 2.0 times 10 to the power minus 13 electron divided by 9.109 times 10 to the power minus 31. You're to get 2.2 times 10 to the power of 17 meters per second squared. Magnitude is this, but direction would be towards the center. Of this circular motion. The question didn't really specify only the magnitude, so you may need to write the direction as well too. Okay. Say if a proton enters the same field with the same speed, what would be its centripetal acceleration? Okay. What you have to remember about the proton and electron relationship is, from chemistry, a little bit of that too, they have exact same charge, but it's simply the opposite. Which means if a charge of the electron is negative 1.602 times 10 to the power minus 19, charge of proton must be positive 1.602 times 10 to the power minus 19. That's it. Okay? Which means that in terms of the force magnitude, it would be the same. Both of the proton and electron will experience the same amount of the force. But this is where the question is coming out from. Mass of the proton, however, in your formula sheet, it's given as 1.673 times 10 to the power minus 27 kg. Compared it to the mass of the electron, which is 10 to the power minus 31. If you remember that, mass of proton is about 2,000 times heavier than mass of the electrons. But you're given the exact value here. That means you can find the acceleration of the centripetal acceleration of the proton by F on mass of the proton, that which is force 10 to the minus 13 divided by 1.673 times 10 to the power minus 27, like that. Okay, now what do you get? 2 times 10 to the power minus 13. That divided by 1.673 and 10 to the power of minus 27. You get 1.195. So given two sigfigs, 1.2 times 10 to the power 14 meters per second squared. Let's compare these two here. This is about what? 1,000 times greater. Sorry, this is 1,000 times greater than this one. What does it mean? What does it mean by that? Carrying the greater centripetal force or centripetal acceleration in terms of its radius then. If you consider that this is the same as V square over R. I'm asking you, what is the relationship between centripetal acceleration to the radius of the circle? Orin, what would be the relationship between centripetal acceleration to the radius of the circle?
Like inverse.
It's inversely proportional. Okay, so which means what? As we have smaller centripetal acceleration, if we have the protons, electrons going to the same field, okay, two things you have to expect. One, electron and proton is positive and negative opposite charge. If we have a magnetic field, this is actually what we had in the HSC question previously, and also for this one too, helium. Remember that helium nucleus is 2 protons and 2 neutrons. So 4 times heavier than the proton and twice greater in charge of the protons too. And the question is actually simply asking you, hey, what do you expect in their trajectory? So, and you need to answer that. It's a 5-marker question. You actually need to answer that too. Oh, because the electron and proton carries the exact same charge but opposite directions. If proton is going into the field, remember that FBI, okay? B going in down. We're now taking the proton in the same direction, the current going this. So move that upwards. So we'll move upwards, or making this direction of the anti-clockwise circular motions. What about electron? We go downwards. Does it make sense? There was 1 mark. 2, in terms of the radius, as we discussed that, greater the centripetal acceleration, centripetal acceleration. I'm not concerned about mass here. Greater centripetal acceleration means what? Smaller. So AC means smaller the radius. So as we have a greater the acceleration of the electrons than the protons, the size of circle must be smaller than size of the circle made by the circular motion made by the proton. That was 2. The question also asks you about helium then. Without doing any calculation, guys, then, okay, what would be the trajectory, the pathway of the helium compared to proton? First, it will move in the same direction, which is going upwards, which is going in the anti-clockwise direction, because both of the helium and proton carries the same amount of a positive charge. But in terms of the radius, yeah, that was a trick. There was a thing that actually people needed to think about it here. Helium carries the helium is 4 times heavier than the proton. How does that affect the acceleration then? As we know, A is expanded by F on M. If they receive the same amount of force, not even the same amount of force, and force is carried by QVB sine theta, then helium carries 2 charges, twice greater than the proton. So force on the proton and compared force of the helium, comparing these two, this is greater, or you can say this is 2 times force of the proton due to that the charge of the 1 plus and 2 plus. Does it make sense to all here? Then what happens to the acceleration? Then AC from the proton is the force of the proton divided by mass of the proton. Okay, what about force of the helium? This is a force of the helium divided by mass of the helium. But in that case here, the force of the helium is 2 times F of the proton. Make sense? Okay. But what about mass of the helium? 4 times mass of the proton there. You cancel out, you get the half of the proton, the mass of the proton there. So in fact, the acceleration, the centripetal acceleration of the proton is twice of the, it's actually 2. It's a half of, the helium, I should say, the proton heat, okay? So acceleration centripetal acceleration due to the helium is half of the acceleration due to the proton there. That was the question. Okay, and it was expected, pre-assumed knowledge that you know what the helium is, helium nucleus is, or the alpha particle is. Does it make sense? So in fact, you would think like, oh, because helium is heavy, helium carries a greater charge than the protons, you would make like a more greater, like in some smaller charges, but you need to actually prove that quantitatively without giving any values like this. This is what I mean by you need to use some mathematical expression to back it up, back your data, so back your answer. So what happens to that? Remember that greater the centripetal acceleration means that smaller the radius. As we have carried a greater of that, the size of the helium is actually moving smaller in this case due to the mass and the protony. Is it too difficult to understand, to be honest? Like, I mean, if you think about it in here, oh, okay, that makes sense. And everything started from here. Oh, that makes sense. That's logically making sense. But when I'm giving you that in the exam paper, the way you need to express your answer is a totally different story. Okay? Because I will give you that. And you will see that question in your, maybe you will see that in like one stage of your HSC preparation. Many questions relate to that. And remember that it was 2020 HSC question 32 or 33. 5 marks, bam. See, I haven't used anything new. This is all you learned before. Any questions up to here? Does it see? We got to determine, let's quickly do the determine directions. Let's do easy way, okay? If you read that, you have an electron, use your left. If you read that, you have a proton on the current, use your right. That's it, okay? Left or right or left. Magnetic fields into the page, electron entering from the left. So, electron, left, okay? FBI, just if you're not too sure about it, FBI, just pronounce that. B goes in, I goes that, goes like this. That's it, easy. Okay, you don't need to prove that Y is this, you just need to show the direction. Next, magnetic field down the page, electron entering from the left. Again, electron, FBI on your left, FBI. Remember that, start from the middle finger, FBI, okay? Going down, I that, coming, it's out of the page. So it'll make it out of the page. Straight away. Magnetic field out of the page. Now, proton. Now, this time it's not perfectly 90 degrees. It's kind of obliquely like going, making some angles too. Let us think about it in here. Does it really matter for the angles, like of the entering that? I mean, this angle. So, guys, this is what you need to actually think. Okay, think about it here. My black pen is representing the direction of the magnetic field, which is what? Coming out of the page. Okay, so this is coming out of the page. Look at the cap that's coming out of the page. My blue cap is representing the direction of the proton in this case here. So it says it's going into this angle, like this. So see that? It's going like this. Can you see that? So can you see that here? Now, let's see what angles they're making. They're making the 90 degrees. Oh. Do it again. Coming out of the page, into the page, yeah? Follow the angle, follow the direction. See that? Making them 90 degrees. This is a trick question that you have to concern in here. That it doesn't really matter, like in terms, as long as from this side over here, it doesn't really matter, like go up and down. It will only change. We only count the angle when they started making this. Does it make sense? Which means that if the electron or proton is going into the out of the page, follows the same direction of the magnetic field, then we would consider about theta, sine theta, because it will have less impact on the protons moving. So let's consider about the direction then. Proton, right. Okay, dominant hand. F, B, I again too. B coming out of the page. I going like this. So where you see the middle finger going downwards. So you're making this circular motions, which is what? Clockwise in our perspective. So easy. Okay, I will post the rest answer for the 9, 10, 8, 9, 10, 11, or any questions about that? 10? So I told you 10 is the type of questions I kind of discussed. 11, yeah, kind of similar questions too. Any questions up to here?
No.
Okay. So what I do is I will give you some prints of the past HSC questions now, and this will be your homework, one of your homeworks for this week. So there'll be quite a bit of homework you need to do. Just couldn't finish there. And for these questions, I will put it up in the class 365. You can download it again if you lost one. And those in the joining us online, you can download that too. And make sure you do it. And I will go through a few of questions today only on your view. But well, this is pretty much it for the HSC type. Okay. Give me a sec. So 2. Okay, have a short break on while we're having waiting for the print. I'll revise that. We actually had like in 2 years ago, Steph, I conducted an experiment from electromagnetic field from making the sound wave. So it was actually, in other words, I made a microphone. Yeah, and well, she got like a full mark for that because no one actually made that before, and people actually made a guitar using that. It was quite fascinating. But yeah, stick on to the scales. That's fine. You don't need to make a microphone. But if you're interested, like about the report, I can share that. The person who got a full mark, it was James Roos, by the way, and she was so happy for that report. I was happy too. Actually, I need to give a cover of this question as well. Give me a sec. quite thick. I forgot how many questions there. Okay, yeah. This is collection of the 2000, starting from 19, 20, 21, 4 years worth of the HSC question, only for chapter 1. Okay, so from this, what I like to see now is, let's do some, give me a sec. HSC questions by chapters, here we go. From that, I would like you to have a look at the, let's do, start from the easy one. Question 22, please. 2019 HSC question 33, it was 19 and 4 marks actually. Okay, that's what I mean by that. This is basically the answer for that, all the electrons do. Okay, let's have a read the question. I'm not, you can do that for your homework. You can just write it down, the answers. But when you're answering the questions, especially the HSC questions, guys, okay, I never said this is a closed book, and this is not a topic test or like some sort of test. Means I really want you to write an answer to get 4 out of 4 because it will be marked. Okay, so let's have a read the question 22. A proton and an alpha particle are fired into a uniform magnetic field with the same speed from the opposite sides as shown. Their trajectories are initially perpendicular to the field. Explain one similarity and one difference in their trajectories as they move in the magnetic field. So what we have, we are given proton and alpha particles. Okay, Orin and Steph, can you think about, I mean, I gave you some kind of guideline how to answer that question, but can you give me about 10 or 20 seconds, think about why this question is worth 4 marks? So that you can get 4 out of 4. Okay, Orin, why would it be a 4?
Like the one similarity.
Mm-hmm.
You have to like, I guess you have to get it right, and you have to like explain it well.
Okay, so one identifications, one justifications.
And I guess what difference would be like the same. I get the justify.
One identification, one justification. That's it. Yeah. This is why I only gave it 10 seconds. As soon as you see it, like it's kind of bold, it's actually given in the capital letters. Can you see that? Okay, this is the key. Highlight it. Use you bring your highlighter in it. Highlight that what you need to answer for, and highlight the marks, which is a 4. That's giving you that, kind of guiding you how to answer the question so that you can save your time. 4 marks in HS means that you only have up to 7 minutes. Okay, if you start spending more than 7 minutes for 4-mark question, that means you're losing your time. You're gonna run out of time for some other questions, and you will lose your time to checking your answers too. So if you have a stopwatch with you, and you can just, as soon as start the questions, reading will take about, depends on the question, about 30 seconds. But if you need to read through it again, spend your time, okay? Or you can use your reading time. Don't just sit down and watch the clock on your 5 minutes reading time. Please don't, okay? There are some questions that you need to require some comprehensions. Spare the time, okay? Or start with the question as soon as you start your exam, okay? For the longer statements. You're right. One similarities, just one, it means it could be out of many, okay? One similarity, what do we have? Alpha particle and proton, which is both are positively charged. Do you think to effectively identify the similarities, do you think you need to identify what the alpha particle is? You can't assume that the examiner will know. Of course I know what the alpha particle is, but I want to see that you know about the alpha particle. So do you think you need to define what the alpha particle is? You do. What is alpha particle? That's a helium nucleus. What is a helium nucleus? It's made of 2 protons and 2 neutrons, or describe that as it's twice heavier, so it carries twice charge of the protons, 4 times heavier than the proton. That's what you need to say. Okay, started with that kind of introduction. You're going to introduce about proton and alpha particle, and then talk about similarities. Both of them having what? Same positive charge. That's a similarity. Therefore, in terms of the trajectory, you've got to talk about trajectory, not the positive charges. Okay, the direction of the trajectory will be decided by their what? Their charges, or like their characteristics of charges. As they have the same charge of positive, they will have this similar same direction of the trajectory. In this case, and you can determine the direction by using the right-hand palm rule. If you can write that in the side note, why not? HSC, your last exam. You never get a physics exam unless you study physics in the university. Write everything you know. Okay? So that's pretty much the similarities in this case. What about differences? There are lots of differences we can talk about it here. Step, what would be the main differences between the trajectory of the protons and alpha particle? Why? Yeah. No. This. Yeah. Pretty much. Or you can just state why in terms of like, because you don't have to say, but guys, you don't have to say, oh, the trajectory of the helium would be half of the trajectory of the protons, because the question can really ask you like it's quantitatively here. You can just generally speaking that, oh, the trajectory of the proton size, or the radius of the protons, the circular motion would be different too. This trajectory of the helium, because they have a mass and the charge differences. And do you think you need to show any relevant any relevant physics formula to back your like answer up? Yes, you do. I mean that. Is it hard to write that? Everyone agree that, oh, this is actually doable. Okay, but think about when you have HSC question. And sometimes it's really hard to attain the 1 mark. You actually need to write quite a lot to get a 1 out of 4. Because some people write in a really good manner, like showing all the details. That's how we take the band 6 standard. But once I set the band 6 standards, then rest of those standard below that would be like band 5. Means easy question, probably one of the easiest question ever. But if you get a 3 out of 4, you have no chance to get a band 6. Remember that the raw marks required to get the band 6 this year was around 80 above, 85. We have to figure it out too, but it will be like somewhat similar to 80 something. Last year, year before, 2023, raw mark to get the band 6, 2023, the easiest paper ever was 89. So if you lose 1 mark and you hit this kind of questions, sorry, no chance. Okay, so be aware of that. What about this one? 23. So what I do is I will post up this paper now. So Kevin, you can download that paper, or Andy, if you're in there, or anyone. So I would like to try that question. This is question 30, 2021, in total of the 5 marks. So I give you about 6 minutes, 7 minutes. Okay, I'm posting this one now, so you should be able to get this in a minute. And again, it is your responsibility that you're gonna catch all that missing work if you're in your holiday. Kevin or Andy, you can download that on class 365 resources part. Please do. And yeah. And now do question 23, if I'm correct. Yeah, 23. No, I'm just checking the lighting here. Sorry, should I install the extra light? Because the screen usually was a little dark. Sorry, but it's major work if I just install it like this. I'm thinking what I can do. All right, how'd you go? Give me. Do you need more time? Again, you really need to think about the mechanics to dealing with some module 6 questions. 2021 HSC question, question 30. So in an experiment, a proton accelerates from the rest between parallel charge plates. The spacing of the plate is 12 centimeters, and the proton is initially positioned at the equal distance from the plate, which is 6 centimeters there. Ignore the effect of gravity. So don't ever use the gravity or G value here. A, the electrical potential energy of the proton is recorded in the following graph for the first 5 centimeters of its motion. On the graph, sketch the corresponding kinetic energy of the proton over the same distance. Guys, what is the relationship between kinetic energy and the potential energy in a given closed system? What is this question about, Orin?
Like, energy is conserved.
Conservation. This is about the conservation energy. And what does it mean by the conservation energy? The total sum of the energy will be conserved in any circumstance, any situation there. Means sum, total energy, would it be? Always be K plus U is the constant. Yep. I mean, is that new? Is it something very new? I mean, I believe you learned that from the year 9 or year 10, the conservation energy, but this is actually a HSC question, year 12. The last final exam paper that you will get in your HSC in your year 12. But we're still using the same rule that conservation energy means that when the K is increased, U must be decreased in terms of the relationship. So how many marks for that? 2 marks, okay? If you knew that, if you noticed that this is the conservation energy question straight away, 2 marks, let me tell you, it only takes 10 seconds. Because if you think about that, at 0 distance, 0 means that it does not have any potential energy. So it will start from 0. When the kinetic energy is reaching to the 0 at this point here, okay, the potential energy will be maximized. So it will goes up to this point over here like that. Okay, and drawing that 2 lines, connect these 2. You see that? Don't extend it further because we don't have any energy to give it after that point over here. What do you say? Oh, that's it. And make sure you label that as a kinetic energy. Don't just draw a line. Please Don't just draw a line and expect to get a full mark. I want you to label that and specifically saying which is kinetic energy like this. 2 marks. 1 mark for the correct shape with the gradient or the graph. 1 mark for the kinetic energy. This is how the markers mark in your work. Yep.
Wait, so for this graph,
Yep.
like the potential energy is not at 0.
Sorry, like it should actually go to this point, following the same gradient. Yep. My bad. This is in my view. Yeah, it'll be like this. Yeah. So which means that when you're adding any of those to kinetic and potential energy, they have the same magnitude. Does it make sense? Okay. B, the experiment is repeated using an electron in the place of the proton. Explain how the motion of the electron would differ from the proton. Again, is that the similar type of question that I have been explaining you today? Asking you the difference between electron and the proton. Okay. What is the main difference between electron and proton? Think about similarities and differences. Having the exact same charge magnitude both, but one is positive, one is negative. And what about in terms of the mass? Mass-wise, proton is about 2,000 times heavier than the electron. Why do we need to concern about that? Because electrons will move first because of the opposite charge. You can think about it here straight away. Electron will move to the opposite direction of the proton because of due to that opposite charge, which is negatively charged. Or we can say electron move towards the positively charged plate, whilst proton will move to a negative charged plate. Too hard? That's easy. That's a common sense by now. Okay. 2. What about, guys, what about the force experienced by both of the proton and electron? Steph, would there be any difference in the force experienced by proton and experienced by the electron? How do you find the force? Oh, come on. You have to graduate that. You have to develop that. F equals 2 in this. Think about here. What are you given? Oh, you sure? Are you sure? Read, please. This is what you need to process here. You're not given any magnetic field, do you? Are you given any magnetic field? What are you given? Can you read the question and tell me like what the answer is? I really want you to process that. Because I can't be next to you and telling you, no, F is not equals yes, F equals ma, but I'm looking for something else. What is it? What do you have? What do you have? Orion, what are you given? Charge and? What does it mean by this? Oh, come on. Parallel plates. Are we given electric field or magnetic field? Electric field. I've been talking about electric field the whole time. It's given here electric potential energy even here. Step, am I talking about magnetic field? Can I then use QVV? No. This is what I mean like here. Read and process it. Okay? Then what force formula should you think about in related to the electric field? F equals to Q? EQ or QE? Same thing. That's it. My question is that, would there be any difference between the proton and electron, the forces they're experiencing? No, because we discussed it just like 1 minute ago. Q, the magnitude of the proton and electrons are exactly the same. It doesn't really matter about the jump direction. E is same for both. So force must be the same. Yep. But what you can tell about this? Yes, Step. This is now time to use MA. Okay, that acceleration is defined by QE over M. Guys, I'm dealing with the HSC. So you have to really process it. You have to really think about a question here. Mass of the proton is about 2,000 times of the mass of the electron, or simply just greater than mass of the electron. Just think that in here. If they have the same amount of force, okay, or same amount of the F on M, same amount of the QE, by carrying a different mass in here, what would be the acceleration differences? that you have to realize that acceleration is inversely proportional to the mass. So the greater the mass means smaller the acceleration. Smaller the mass means greater the acceleration. So questions asking you, 3 marks, remember that, okay? The acceleration of the electron will be greater than the acceleration of the proton as the mass is smaller. Mass of the electron is smaller than mass of the proton. Did I talk about that before? I did. Did you get a question? How many years? 2 years. Almost like the same question. Any chance you get a HS question this year again too? Positive. This is how you need to analyze the trends of the HSC. And I will help you to analyze that too. And at the end, I will tell you like what questions I'm expecting while I was preparing the HSC later on. Okay? Make sense? Okay. The rest is your homework, and please answer that questions. Before we move on and just have a break. This is 2017 questions. Question 26, please. Okay, once you finish that, have a look at question 26. This is before 2019, but it's well kind of adapted and used in the school trials and now in the HSC. We haven't had this type of style questions again. How many? 4 marks. You don't have to write the answers, but I want you to think about it. Read and analyze the question, please. I'll give you about a minute to think about this question then. Okay, so in a thought experiment, a proton is traveling at a constant velocity in a vacuum with no field present. An electric field and the magnetic fields are turned on at the same time. The fields are uniform in the magnetic magnitude and direction and can be considered to be, okay, please highlight that, considered to be extend infinitely. The velocity of the proton at the instant the fields were turned on in the perpendicular to the fields. So, analyze the motion of the proton after the fields have been turned on. Okay, shall we think about in the presence of the, first, electric field only. Okay, all right, if we have a direction of the electric field going into this direction there, which side will be positive, which side will be negative? If the direction of the field of the electric field is given as this. For the electric field direction.
Right would be positive.
The right would be positive. It flows from right, positive to the negative. Okay, think about here. Plus is okay. Did we do that in year 11? Plus coming out, minus coming in. If you didn't do that, okay, just remember that as plus is coming out, minus is coming in. Okay, or electric field is can flow from the positive to negative. Because, or if you think about it here, electron movement will be opposite to the electric field movement. That electron move from the negative to positive, so it'll be opposite, positive, negative. Or just simply just memorize the electric field from positive to negative. It's not that easy, it's not that difficult. Okay. Now, in the case of here, we have a proton, positively charged, which is moving to this direction. Step. What do you expect for the motion of this proton then? Towards the negative, which means let's give me the direction then. Give me the direction. As the proton enters the electric field, which is going this direction, what happens to the motion? What about the motion of the proton then? Goes, what's it that way? Describe it. No, it's not given anything. West here. It moves to, just simply use right and left. Moves to your left. My right, your left. Okay, we'll just say left. Okay, so it means it moves towards there. Move to the left. Okay, so do you expect if as is given, this field is stretched or like can extend infinitely, what would be the motion of the proton then? It will move to left infinitely. Yeah, just move to left. It's moving the left infinitely. For the electric fields only then. Okay, let's consider about magnetic field then. Again, this is not an answer for this question. I mean, I'm just giving you some clue about how to answer the question. It's your job. You need to answer the question and write in the sentences to get the 4 out of 4. But I give you some explanation before that I give the answer. We have magnetic field going into this direction. Okay, if the proton is again going into this direction there, let's follow that diagram we have. So B is going in east and E going like this. Okay, what do you have to consider? There is proton which is possibly charged, right or left? Right, hand palm rule straight away. Do we know the direction of the magnetic fields? We do. So F, B, I, F, B, I again. B going to the left. I, your thumb up. So what you see there is the middle finger or the palm facing out. So it makes what? It's coming out of the page. Out of the page. Not only that, if you think about it in here, it will make a circular motion. It's coming out of the page and making circular motions going like this. So let's show that. Let me show that again. It goes out and makes circular motions. Can you visualize that? Okay, it's coming out and make this circular motion, out and circular motions like that. Does it make sense to all? Okay. So out of the page and plus the circular motions. Now, let's combine them. What about electric field plus magnetic field in the same time? Not like separate. We have electric magnetic field, which is going in this direction, and electric field also going into the same direction. Okay, proton is moving into across that like this. What about the motion of that? So we're going to combine, as we combine the fields and the affecting fields of protons motion too, we're going to combine these two here. It's very simple if you think about this here. The proton will, first of all, due to the electric field's the effect, it will move left initially. It will move to left if infinitely. Okay, means that it will keep moving left hand side as it's a negatively charged. In the same time, this is making some kind of circular motions coming out of the page. Okay, so let me show you what that means in here. Assume the proton's going in this page. Okay, so what happened is it's making the circular motion with the magnetic field. Can you see this? Okay, I show the motion of this. Whilst making the circular motions, turning left.
Yeah.
What do you say? Kind of spring shape?
Yeah.
Yep. Can you see that movement of the this black cap towards that? It's called also not a helical shape or like just say spring shape. And as the question giving you that this is moving extended infinitely, what happened is it will extend infinitely towards the left, making the circular motions. Analyze the motion of proton after the fields have been turned on. 4 marks. That was the answer for that. So you really need to understand the motion of the charged particle in E field and B field separately. Again, guys, spend more time to study for the charged particle before. And yes, we're moving on to this motor effect today. But as you can see, how many questions did you get? Like in every year, you get at least 2 questions from one chapter, from chapter 1 of the module 6. You will get 1. Not 1, maybe 2, even 3. So we describe the motion as spring-shaped motion, or that's actually a term we describe. What was that? Question 26. We describe a little bit of biology, double helix of the DNA structures too. This is called the helix. It's known as helix shape, like kind of winded spring shape like this. Okay. Oh, one more thing. Because we have a same magnetic field all extended, the radius or the diameter of the circular motion will be also get the same too. Which means we have equal circular, I'm trying my best to draw the equal circular motions like this. And moves goes in this order. So to get a full mark, you actually need to describe that as it's a helix shape. It's moving towards the left. In the same time, the radius or the diameter of the circles are identical. Okay, so this is a typical HSC or some little tricky HSC questions, and then let's just quickly have a look at the question 29. We're not going to solve that. I want to think about a question here. Three charged particles X, Y, and Z traveling along straight parallel trajectories at the same time enters a region in which there is a uniform magnetic field which causes them to follow path shown here. Assume that the particles do not exert any significant forces on each other. And explain the different paths the particle follows through the magnetic fields. So X, Y, and Z, you don't know whether that's a proton, helium nucleus, or the electrons. It's not given. Guys, it's not given. It means you can't use that proton, electron, or even the helium nucleus. You don't know. Okay? But you get the question, 7 marks. Think about it here. This is it. You need to answer the 7-mark question from that given information only. Yeah, I gave you everything. Think about how you're going to 7 out of 7. Why do you think? You got to think about why X and Y and Z has the different trajectories look like that. Okay, what you see there is X and Z have the same radius. Y has a bigger radius. Okay, X and Y have the same pathway, the same direction, whereas Z is going downwards too. So 7 marks. I would like to challenge that question, 7 marks, okay? Finish that within like 10 or 12 minutes. 7 marks, okay. How long do you need to write to get 7 out of 7? You need to write at least a page and a half. Okay, I'll leave that for your homework for next week then. We will actually mark it, give you marks for those HSC questions. And yeah, so you will say that how to get the mean mark. Okay, we'll come back to you. The mean mark, as in like the average for that question was 60%. It was given. So out of 7, 60% is what? 3.5. So average was 3.5. Yes. Can we assume that? Use a ruler. How do you know they're in the same radius? Use a ruler. Show that it's in the same radius. I don't think Y and X and Z has the same radius, but I see that X and Z has the similar or the same radius, approximately, which implies something. Okay? Make sure you show all that relevant working out, including the formulas. I've been saying that every year. Hey guys, just show some formula to back it up. This is the easiest way to back your answers. All right, let's have some break, toilet break. We're going to move on to the chapter 2 then. Oh, if you're looking for some extra questions, by the way, there are a few really good questions at the back of chapter 5, so we can try that. let's start again. I'd like you open your workbook, chapter 2. So we're going to go through those, chapter 2 today. Most likely we're going to finish the whole chapter 2 in the content, and as we did today, we can go through some questions related to some motor effect. And if you want me to, I can revise some of the chapter 1 questions again too, but make sure you finish that HSC. And if you're looking for some extra questions, let me know. Have some more. Okay. All right. Quickly revising that what we learned about charged particles, especially in terms related to like charged particle in the B field, that you need to memorize, understand. Okay, you don't really understand, but you just need to like accept that when there is the for the magnetic field, okay, the same opposite attract, opposites attract, the same side direction will repel. So we learned it from, like, it's given on your revision on, what's the page number? 52. It's showing you that magnetic field is coming out from we believe that north pole. So coming from north to south is coming out from north to south, coming out from north, coming in to the south. But we do not really use a north and south a lot when we're talking about direction later on too, because we rather talk about moving to the left, to the right, to up and down. But what we just consider is if they have the same direction, kind of approaching directions, coming north and north, they will repel. But when we have north and south, which is the opposite directions, they will attract to each other. Okay, so for example, if you have this direction to this direction, okay, what you see there is, you can consider about the kind of vectors too. They will in the kind of opposite, moving in this and that. We'll make a combination of the greater opposite as in north and versus north, and for south versus south, south versus north goes, sorry, other way. North and south will attract, north and north, or the south and south will repel in this case. So in a case but in terms of the direction, this is okay, something that you have to understand in here. In terms of the field lines, when we have the same directions go like that, okay, they'd rather be like more like attracted rather than repelling to each other. Or we can think about having the going up and down, move to the right and right in the same direction. They're more likely to repel to each other too. So something we're going to discuss more in as we go. The second rule to move on to the motor effect is 2. When there is I, the current, okay, there will be, we call that induced, B produced. Induced isn't like it's causing. It's before we have an I, we don't have anything. Like it's, for example, copper wire. Now it's having current flowing. It started building up, inducing some B field too, generating the B field too. So to understand that, we actually use the module 11. So you will see that as we go through that, going into the up and down. Kevin, for the experiment, email me. Don't ask me here now. Okay. Going up there. So what we use is we're using something known as the right hand grip rule to figure out the direction. So if we have a direction going I, go like this. Use your right hand to figure out the directions. Place the right hand simply like this on your page, and you will see that it goes in and out of the page. Now, common thing is as close to the I, the B gets greater. What I mean here is, if we measure the B, we have like a magnetic field generated going up and down like that, okay? Measuring the B field near at the current will be greater than measuring the B field at the back. It's simple as that because it's close to. I mean, I hope you can use some bit of like common sense. Okay, obviously, like it's close to the source of the magnetic field. Another way we can show the direction of this is with using your fingers that is going in and out, like this. Okay, so please remember that this means they're coming in and out of the pages too. Does it make sense to all? Okay, that's where we're up to. That's actually pre-assumed knowledge in year 11. And we actually learned that the B can be calculated by mu naught I on pi r before 2. But we're going to come back to this. This is actually pre-assumed, but if you don't know yet, it's okay. We can do that. So chapter 2, please. And producing that, we're going to come back to this later on. Page 56, please. So last week, we learned about from chapter 1, we learned about what happens to the charged particle in the B field. Steph, what happens to charged particle? Well, let's describe it here. Electrons in B field. What happens to electrons in B field? So, what's the motion? There we go. Again, memorize it. Don't try to understand anything in here. Memorize it. It's just making the circular motion. That's it. That's all you need to say. Making the circular motions. Okay, means we discussed that like, oh, we have a magnetic field goes like this, okay? And when the electron goes in, it's making some sort of, so usually left-hand palm rules, right, FBI or that, it's making that going downwards. We just did that. We did many questions related to this here, okay? But what if we have this? Not just one. Assume that we have a copper wire. Introducing a little bit of a chemistry, copper wire, copper, metals, having the free electron or C of the delocalized electron. I'm simply saying in the dimension of this, we have a lots of the electrons kind of embedded. Does it make sense though? Okay, we can just imagine that, okay. But before we connect that to any of the DC batteries, it just stays stationary like this. I mean, carrying this, even this for now, battery connected, copper, I mean, this is mean by the copper wire. It has some electron coming out, but it's not really connected to each other. So it means it's just the copper electrons inside. And I want you to think about this is kind of narrow channel of the electrons there. It's movement, kind of making the modal waves there. Now, what if electrons then moving connected to the battery, DC battery in the circuit? That's a positive, that's a negative. The flows of the electron would be then moving towards down towards the positive, as we learned. Yep. So let us just think about it here. If the electron moves to this direction, the direction of the current would be I, would be this direction then. Okay, so let's just consider about here. Electrons moving upwards, therefore currents moving downwards, like this. Think about here. If we extend the magnetic field like this, okay, first of all, you'd expect that electrons will move, having some kind of what? Circular motions again too. We have a charged particle in the B field that's having a circular motions. So what would be the motion of the electrons if they're kind of embedded inside? They come ejected out of the copper wire. They're kind of capped. Means I can use my left-hand palm rule here again too. F, B, and I. The electrons are moving upwards. B is going downward like this too. The electron will try to move towards this direction. In terms of force. Okay? That's only if when we connect that to the battery. Does it make sense? Which means as electrons, you can imagine that electrons now kind of moved upward in the same time because of the interaction to the B field, kind of pushing. So you actually see that the wire started moving to this direction as well too. Okay, this is the one explanation that I can explain about something known as the mortar effect. And this is a thing that we're using to build the mortar like this. What you see there is copper wires, winded, magnets inside too. You see that when this is connected to the battery, you will see this is started to rotating. And we're going to talk about the DC motors later on too. So putting this is rotating. This is called a motor, by the way, okay? But only have, this is what I mean here. If I connect it to the battery here, even though it has electrons embedded inside there, it doesn't really make a movement at all. It starts a movement when I connect it to the DC battery, like this. Other way. Probably, sorry. Oh, okay. Now, I'll show you this. So, magnetic field is installed, and so connected to the battery. See the movement. Now, without the magnets then. So, without the magnets, see, you wouldn't see, obviously, any movement of the motor. Okay, which means to produce some kind of the force or the magnet, some kind of motor or the motion, we need to have some combination of the not only the electricity, you also need to combine that with the magnetic field, like this, so that you're able to see the rotation of the motor too. This is why we can actually name that as motor, as from the motor, because it's from the motor effect. So this is the first explanation, but I know it's kind of tricky to think about electrons every single time too. So what I do is I'm going to just introduce a really simple way to understand. I mean, you don't have to understand it again too, but you're going to think about it in here. That means that if we have an external B field, so that was an external B field. The way you can think about external B field is simply this magnetic field. Guys, this magnetic field, this magnets. It's a north and south, means magnetic field has a certain direction going this direction, or maybe in another direction too. Okay, that's what I mean by external B field. Does it make sense? Okay. Now, having the current carrying wire as a wire. Now, as we discussed from the before, when there is I, it will produce B. So assume that this has the current flowing to this direction I. Okay, I'm just simply using this one here. And we learned that current will determine like the direction of the current will be determined by thumb. Fingers will determine the something known as the induced B field. So using that again, I show you this will generate the magnetic field, which is going in and out like this. Okay, but instead of using a circular shape, I can describe that as this going into the page, coming out of the page. Makes sense? It's nothing new. Nothing new. But what if we extend the B field to this side, even further to this side there? Then, all right, what do you expect for the interaction between two magnetic fields? Remember that one from this kind of external magnetic field, one is from the induced, the B field. What would be the interaction between the magnetic fields then? Well, some side will repel, some side will attract. Remember that the opposite attract, the same side will repel. The simple rule of the magnetism. What we see there is, you see the same axis. Same axis, same side. So there will be our repulsion. Simple as that, okay? What about side here? We have the attract side, attraction. Then, think about it here. On the side, on the right-hand side, it's kind of repelling. On the side of the left, it's kind of attracting the wire. Means that we will have the same in the simultaneous repulsive and attractive force, therefore inducing this to be moved towards to this side there. Does it make sense? Another side is kind of, you can imagine pushing, and this kind of pulling, repulsion and attraction. So this makes that to move towards this side, and this is called the mortar effect. And obviously, electrons inside are kind of moving towards to each other too, in case of those. But does it follow what I just explained to you? Because when the current's going upwards there, electrons are moving downwards. Means the electrons kind of pushing that wires towards the left-hand side. This is how you need to understand, but you don't have to use that to understand the point. All you just need to think about it in here is, yeah, okay, this current will produce some induced magnetic field, and because of the interaction towards that external magnetic field, so what that means is, when I follow the currents inside there, it will start having some direction of the magnetic field kind of induced in the coil. And because of the interaction between the coil's magnetic field to the external magnetic field from this one, it started moving the one direction. Yes, Steph? X means going into the page. No, magnetic field. Magnets. X just stands for the direction. So remember that. X means into the page, dot means out of the page. That is, it's the same as I'm using arrows to describe the direction too. I can't describe that it's going into the page using the arrows, can I? So this is why we're using we kind of promised that X is going into the page and dot is coming out of the page. And you see quite a lot. Did we see that like the last lesson too? I'm pretty sure we went through that. And stop your thinking that what produced the magnetic field. Just think that it's a magnet. It's a magnet. Magnet. Attracted to support too, okay? This is the point that you don't need to understand everything yet. There'll be a point, because if you start thinking about this too much now, you will get confused, you get trapped in induction in chapter 3 and 4. So I try to make your job easy. Don't think about it, don't try to understand everything in here. If you really need to, you may consider about charged particle there, which is electrons moving downwards, they've been pushing that too. You may go up to there, but I would like to stop your process, because it will be getting more complicated. But does it make sense? I'm simply just combining these two to explain why we get some motion of the wire. Does it make sense still? Okay. Then how do we use that to figure out? So page 57, please. This is how we can get the mathematically then. Now from year 11 or from somewhere else, maybe from like, I don't know, from year 9, for electricity, page number 57, please. We define that. Do you remember that I, we define that as quantity of the electrons, or having the greater number of the electrons carrying, like moving, means the decided amount of the current too. So for example, 10 amps to the 1 amp, it will have the greater amount of the electrons inside there too. So mathematically, it's defined as the amount of the charge Q on the T like this. Okay, should be given on your formula sheet if you want to confirm that. I equals Q on T, yes. What that means is amount of the charge divided by the given certain period of time. This is nothing new. This is something we'll probably learned. We did that in year 11 as well too. So I'm not going to spend too much to explain that, why I equals Q and T, or just consider that Q means that amount of charge. So it depends on how many electrons we have. It will decide the amount of the charges too, because each of the electron is quantitatively carrying very specific number of the 1.642 times 10 to the minus 19 charges. So having 110, decide the amount of charge. Okay. Now, I is defined by Q on the T. You can write it down. So it means that it's given here let's copy that, for a 1 meter length of conductor. Let's assume that we have a 1 meter. So 1 meter is, this is a meter ruler. It's a meter of the conductor. I have this meter of the conductor there. Okay. Now, using the sum of bit of velocity constant too, the velocity of the charge can be calculated by the V, or as you know, distance. As you know, distance can be calculated by what? The velocity or the speed, sorry, it should be speed, times the time. Okay, then the velocity or the speed is found by distance over the time like this. Nothing new, okay? Then for 1 meter length of a conductor, then the speed can be seen as 1 meter divided by the t, like can be like right here. In other words, v is in this case is 1 over t. Only for this, because we made an assumption that for 1 meter length of the conductor. Okay? Then, as we're given here, can we then substitute that back into the I? Assume this is equation 1, equation 2, equation 1 into 2. Then you to get I is equals to now, as v is equals to 1 over t, it's simply qv. Everyone good up to this point? Yeah, I mean, like, this is simple math. Yep, good. Then let's bring it out. What we know, for the charged particles in the B field, the force was calculated by QVB sine theta, wasn't it? Okay, equation 3. What you see there, equation 3 and 4, I should say. Can you see that QV and QV is a common between 2? So can I just substitute that F is then equals to I times B? So it's the same as that, the sine theta. But inside of that, the QV, we already can make an assumption that this is for the 1 meter. So what I need to do is the same as I times B times 1 meter times sine theta. Does it make sense though? But we know when you're dealing with the 1 meter every single time, I mean, it's rarely we get to 1 meter of conductors, which means the length of the wire would be variable. So what I do is, instead of the 1 meter, leaving the 1 meter there, I make it a proper, like a generalized formula, that is B times I times L times sine theta. And that's known as the force. This is the new formula that you need to memorize. And what is this about? This is not a charged particle in the B field. This is about the current carrying conductor. So write it down as, this is a force generated for a current carrying conductor in an external magnetic field. Okay, and this is known as the motor effect. Here, equation 3, this here, I is equals to Q over T, V is equals to 1 over T. Come on, for you people. Come on, for you people. That's all I can say. Okay, simple deriving from that. And it's quite smart. They actually how they thought about making the formulas in physics. People actually use quite a lot of assumptions. So F equals to BIL. This is different to the F equals to QVV sine theta. It's originated from the QVV sine theta, which is charged particle in the external B field. So it kind of tells you that the relationship between the two, that charged particle in the B field would now experience some force. As what we discussed that before. If we extend that, lots of the electrons inside there too, and they're kind of carried in the small length of the diameter of the wire, they would now have the motion moving. So considering that here, can we now, this is for the magnitude, by the way. This is for the magnitude of the force that it would have experienced. Can we use the same rules that to determine, which is the right-hand palm rule, to determine the direction of the wire? You can. Okay, so plus direction by right-hand palm rule. So let's consider about the situation that we're given on page 57 over here. Okay, you see this have a north and south. So okay, the way you can determine the direction of the magnetic field is always from north to south. Okay, so this is the direction of the B. You see the direction of the I go like this. Then what you see, you can see the I, which is should we use right hand and left? If you see the I, there's a positive, use your right hand palm rule. You can't use negative. You can use the left hand for this. Okay. So again, F, B, and I. F, B, and I, or F, B, and I, whatever. Okay. So B is coming out of the page. I is going this page there too. That means what? It will make this the wire to move downward. How do I get that? Use your right hand, please. FBI or FBI. B is coming out of the page. I is moving to this side there too. Okay, so you show the middle finger or your palm facing down. That's how we can get it. But if we have a situation that the current is flowing the same direction of the magnetic field, that means that they would not interact to each other, so that force will be zero in this case. Just like the same as what we discussed in the charged particle in the B field too. And this is why I spent quite a bit of time to explain you what happens charged particle in the B field. Because they shares, actually in this coming from the same root, why you're moving in such a direction. So 2.1, let's do this question then. Determine the magnitude of the force due to the Earth's magnetic field that acts on suspended power line running east-west near the equator. At the moment, it carries the current of the 100 ampere from the west to east. Assume that the strength of the Earth's magnetic field is given as that. Okay, all right, guys. When we heard North Pole and the South Pole, I hope you learned that before, or if you're not, please remember that. Okay, when you're saying the North and South Pole on the Earth, okay, yes, we generally saying North is the one exerting the magnetic field, South is the one that accepting, receiving the magnetic field. But only for the Earth's equator, okay, we know that South Pole is the one that exerting, and North Pole is the accepting that for Earth only. Memorize it. There's nothing you have to understand from here. It's simply like, I don't know why we started confusing the South and North, but we believe that. I mean, this is why your compass shows the South and North in this reason too. But the direction of the magnetic field on the Earth is from south to north, like this. So this would be your external B field. All right, let's follow the question again too. Then what we have is a suspended line running east-west, from east to west, and the equator. At the moment, it carries a current 100 amps from west to east. So from west to east, the current is going into this direction like this. Okay, I just followed what the question is given here. So what you see there is, you will see that this magnetic field, as well as, excuse me, the current will now interact. You don't have to find the direction because the question simply asks you to find the magnitude. So what we can do then, F is equals to BIL sine theta. Bring that up. Theta in this case would be 90 degrees, so making sine theta to be 1. So therefore, force is then given magnetic field by 5.0 times 10 to the minus 5. I was given as 100. Now, what you're not given is the length of the wire. So I just leave that as L for now. Okay, or to say in the meter forms. Then this gives you this. Calculator. 5 times 10 to the power minus 5, that times 100. It gives you 0.005 times the length. You do not need to find the length because you're really not given the force. So what you can tell is it'll be 0.05 newtons per 1 meter. Does it make sense? Okay, if the L is at 1, that force would be 0.005 newton. In other words, we can rewrite that as 0.005 newtons per meter like this. This is how you can write the new units if you're not given the something the units of the, or like the actual length of the wire. So that'll be the magnitude. Now, what about the direction? So simply use right-hand palmer again, F, B, and I. Okay, B is going up, I is going into this direction. Force would be coming out of the page. So you just say the force coming out of the page, or saying dot would be the direction of the force in this case. Means that I want you to imagine that, because we actually had a HSC question about it. You have a wire, suspended wire, on the ground. Okay, what does it mean by the direction here then? On the earth, you're here, this is suspended wire, and you're like standing like this. Okay, at the equator. So you will see that that's a wire at the equator, and we're seeing that current is flowing from this direction, whilst we're having the magnetic field going into this direction. So when you say, it's easy to say coming out of the page in our view, okay, in here. So you just say that direction would be coming out. What that means is you actually see that on your perspective, or if you're standing on the equator, you start to see that wire is coming popping out of the front of the ground. So in your perspective, it'll be upwards. Okay, so a bit of imagination required to understand the question here. Make sense? Okay. 2.2. Amundsen Scott South Pole Station sits at the point that can be considered to be on Earth's southern magnetic poles, so which behaves like a north pole of the magnet. Again, south of the Earth's pole means that it's working as a north of the magnet. So it's working as a north. Don't confuse that, and don't ask me why. Like this is a bit of a historical background of that too. It is just accepted. It is just what it is. Okay. Then, assuming the strength of the Earth's magnetic field is given at 5 times 10 to the minus 5, determine A, the magnetic force on the 2-meter length of wire carrying a conventional current of 10 amps vertically up the exterior wall of one of the buildings. So what that means is we have a south pole, we have a building, let's say, or like some house or whatever, okay? We have a wire, it's vertically, just give it that, vertically up exterior wall, vertically up exterior wall. So in our perspective, again, we are standing like this in the south pole, okay? Vertically up means this is your wire. All right. That means, what do you see? Yes, magnetic field in this case will coming out from south. So it will actually, in our perspective, it seems like coming this direction because it's going towards the north like that. So what you see there is, even though the current is flowing in this direction, like in here, the current flows in the conventional I. Can you see that? Can you imagine this? Okay. Can we say the I angle made by I and the B is 180 or 0? That means as sine 180 or sine 0 is 0. Therefore, force would be 0 too. And this is actually a real thing, guys. In the South Pole, like in their and in their stations, they do not actually put the wires in the horizontally in that reason. They actually put it vertically. Scientifically proven, though. Doesn't matter. Like if going up and down, like you could go up and down, but doesn't matter for like in terms of direction. I mean, I is going up or down. B is down. what's the angle made by these two lines? Sine 0 is? Force would it be? Thank you. B. What if we have a situation that we have a current now going into the horizontally from right to left? It's given right to left. That's a current. Oh, sorry, I should use the blue. That's a current, B. At the same time, in your perspective, B is going downward direction like this. Okay, I'm just following what the question is giving you here. So let's find that first of all, the magnitude. The theta is in this case 90 degrees. Angle made by the current and the magnetic field. Oh, sorry, that should be I. Current and the magnetic field is 90 degrees. So F equals to BIL sine theta. The B is given as, what's the lab B given? 5.0 times 10 to the power minus 5. The length of wire that was given as 2. And sorry, the current was actually given as 10. I missed that. And sine 90 would be 1. So you can ignore the value. So 2 times 5 times 2 times 5 times times 20, you would get 0.001 Newton. What would be the direction then? You can use your right hand palm rule again too. Yeah, you must use it. Don't use your imaginary right hand in your hand, guys. Really need to use it. F, B, I, B going down, I going this direction. So you will see that it will have the direction of force coming out of the page. What that means is if you're standing here like that, so that's Earth's crust, then you will see that like opposite that too in the South Pole. Okay, South Pole. You would start to see like the wires kind of popping out, and because we had a constant force of 0.01 Newton. The greater the, imagine here, in that scientific station, they actually use huge amount of current. They're not only using the 100 amps probably, or 10 amps, they might use up to 100 amps too, because they have to run the really heavy vehicles too. So if they start building up that wire in horizontally, that means that there will be some destruction of the whole machineries in that too. So this is actually what they investigated. They actually things happen and they just investigated through, and that's what they found out in the South Pole. Okay, it's quite interesting once you understand what is going on there. Let's do one more. Page 61. You're going to skip a few questions there before. Could you answer 2.4? I give you about a minute. It's an easy question. That's supposed to be IL. All right, 2.4. The force of a 10 centimeter wire carrying a current of the 15 amps when placed in the magnetic field perpendicular to the B has a maximum value of the 3.5 Newton. What is the strength of the magnetic field? So for this type of questions, okay, if you're confident, you can just substitute like all the values in, but if you're not, especially if you're making lots of mistakes, write it down all that relevant information that you get. So including L is given at 10 centimeters, and this is a thing that you can commonly make the mistakes. Make sure you convert that into the standard unit of the meter. That is 0.1 meter straight away. I was given at 15 amps, that's given. And what you're given is force, what's given at 3.5 Newton. At the same time, the theta is 90 degrees like this. Once you're given up to this stage here, you know that F equals to BIL sine theta. Okay, to make a subject to, there's something that you want to you want to find, which is B. The subject of B would be F on IL sine theta, and simply substitute all the values in. That you have 3.5 divided by I, 15 times 0.1 times sine 90, which is 1. Okay, then you get 3.5 divided by 15 and 0.1. You should get 2.3. And given 6 equals 2, it's actually 1, all from 10 centimeters, but I don't like to say that 1 suffix at all. So just 2.3 units, Tesla T. Remember those. Easy. How easy is this? Okay. Yes, I just gave you some practice, like an easy question about F equals BIL sine theta. I'm going to bring some questions about in HSC, how we actually manipulate the questions too. Any questions up to here? F equals BIL? Step you could, okay? This is the thing you actually need to use to do for your experiment too. One thing, okay? Second is, what if we have, sometimes we have the conductors saying, we don't have any external magnetic field. Now we learned that when there's I, we will produce the induced B. Means that technically, when you have two separate conductors, both of the ions, if they're flowing current, they are able to get like some kind of interact to each other. So I'll show you that one experiment in MIT. Been using, showing that. The reason why I can't do it in here because it requires a bit of a high voltage, and because of safety issues, use the high voltage. Actually, I can do, but let's see. So what you see there is, depends on the direction of the current that's in series or parallel. You see that there's nothing else. Just the current flows start flowing into the two wires. You start seeing they're kind of attracting or repelling to each other. Okay. Now let's talk about it in terms of series and parallel. Then it's also given on your page 62 that we kind of described it before too. Okay. Now, when we in the situation that I have that this in series, so what we have now is we have a current that goes I1 and say I2. It may be same, it may not be different, it may not be same. So it doesn't really matter for the strength in here. Then what you just need to remember is when there's I, there will be induced B. Okay, and how do we figure out the direction of the induced B field? Using your right hand grip rule. So how do I use it? If you know the direction is going upward like this, show that. Okay, so that direction of the magnetic field, the first one would be that's going into the page. On this side here, coming out of the page. Nothing hard. Use your fingers. Okay, show the direction there. What about the second one? It shows you that the direction of the magnetic field in this case is coming out of the page on the right-hand side into the page. Okay, and we learned that today, I mean from many times. The opposites attract. The opposite field direction attracts to each other. So what happened between these two? There will be, this side will attract, producing the force towards each other like this. In a case of that, we're going to actually need to use some of the action and reaction forces. That amount of force generated from here must be the same as the amount of force generated from the other side there too, according to Newton's third law. Does it make sense? Okay, so it means that in a series, they're all in the current in the same direction. You're seeing that they will attraction. And this is the explanation why they attract to each other. Parallel, then you can just easily guess that if current goes into one going up, another goes down, I1 and I2 like this. Okay, that means that you can figure out the direction of the magnetic from the I1 would it be same as the previous one too. So going out of the page, X into the page. On this side over here, would it be same? It's really coming. See that? This side coming into the page, so you go into the page, coming out of the page, like this, and you see that this too will now have the same direction of the magnetic field, therefore producing the force outwards, repelling to each other. So this is a case where currents in the opposite direction will make a repulsion. The key word would be this: the opposite, repel. Same, attract, for this type of question then. I mean, I know most of the time we say opposite attract, the same side we would repel, but there's a way you can, I really ask you to like memorize that as like some sort of template. If you're seeing that current going in the same direction, they will attract. Current going in the opposite direction, they repel. And this is something that you're going to use, Cumberland High Schools, you're going to use in your practical task as well too. It's for the it's actually previous one as well too. You can actually use two current conductor wires, make them to repel to each other, or like you can put a couple of wire on the scales, put a wire current flowing on the top, and you'd expect to see like some difference between those, the mass increase and decrease in masses too. Again, I can show you that a HSC or some practical practice questions that you can referring to for your prac. But before that, this is why you need to understand the theory and how to calculate the values. Does it make sense? Okay. Now, again, this is for the directions only, which means that you're actually able to find that the forces between them in terms of in their magnitude. This is given on your page 63. That's given as here. So in year 11, we learned that induced B field, B magnitude, was calculated by this. It's known as mu naught I on 2 pi r. That's actually what we learned. I mean, it's kind of pre-assumed knowledge too, but if you haven't learned that, haven't heard about it too, it doesn't really matter. We can start a refresh too. I'm just giving you the B. It's because I said whenever you have an I or current flowing, there will be an induced B field. Okay, this is how you can find the B field strength, where R is the distance from the I or the source. Mu naught is simply a constant value, like a pi. You can just think of it as a pi value, like a 3.14. It's known as the permeability constant. And that should be given as 1.257 times 10 to the power of the minus 6. I just follow that given here. This will be given as well in your formula sheets. You don't need to memorize this value. Okay, don't bother to. 2 pi is what? Just a pi times 2. What about 2 pi r? Orin, what is the 2 pi r referring to? Circumference of the circle. Why we say we find using the circumference of the circle? Because when the magnetic field is produced, it will making a circular shape like this. So what I mean by this is R. And circumference of the actually giving you the radius or like a range of the magnetic field is kind of produced. From that, mu times I, that is the actual magnitude of the strongest magnitude. So as R is getting decreased means that as R is getting decreased, you would expect to get B would get increased in this case. In other words, if you're measuring the magnetic field near at the source, near at the eye, this is the strongest. Out of the range, if you're measuring the magnetic field out of the here, of course, you wouldn't see like much of the magnetic field due to that too. Okay, you don't need to like really know why the 2 pi r comes along to, but this is actually what they found out before. And as I said, it's from year 11, a little bit of year 11. Now, thing is this, assume that we have attraction. Okay, so which means when both of them on this side and this side over here, we'll start having some force kind of magnetic is generated. So what do we have is first we have a force 1 that's from the this I1 here is by B, sorry, not the force, B1, which is induced magnetic field from the first current would be same as mu naught times I1 times 2 pi and R. Just following the formulas that we learned. Same for the second one. Second one is B2. That's a mu naught I2 over 2 pi R as well too. So let us consider a bad situation here. This is producing the magnetic field look like this. At the same time going in and out. At the same time this is producing magnetic field going in and out too. So when we're talking about R, we are talking about R would be equal distance from both sources then. Does it make sense? We are not talking about some of the greater distance between two, which means from one to another, I'm talking about these two. They are the same R distance given over here like this. Does it make sense? Now, because what we know that is these two will interact to each other, according to the Newton's third law. What is what? Action and the reaction. That when we have an action force applied, there will be an equal amount of the reaction in the opposite direction. That's like Newton's third law. When they're having some applying some action force, we're looking at the one side of the I1. When this is applying, when I1 applies the F1 to the I2 side, okay, there will be the same amount but opposite direction force of F2 generated. In other words, F1 in terms of magnitude equals to F2, given here like that. Does it make sense? Then, how do we know the forces are generated to? The force is then can be calculated here because we are talking about the interaction between two magnetic fields. The force is therefore, then can be found like this. Mu naught over 2 pi R times that, the I1 times I2. This is known as the force generated between two. Oh, sorry. Or hang on. Force becomes B1 times B2. So writing that, we have mu naught I1 over 2 pi R times mu naught times I2 over 2 pi R. It gives you this. It's actually giving us slightly different values. Into permitted. Oh. That's just, it's been a while. Oh, it gives you this. Kind of rearranging that to pi equal to pi. This gives you mu naught I1 I2 over 4 pi r squared given as that too. Kind of rearranging that because they're canceling out some of the magnetic field, so we can ignore the 1 mu naught is cancelled, the 1 pi is cancelled for that the interactions. This is known as the force between them. But imagine this: if y have greater length of this, of course, as we discussed before, like it will have a greater amount of force induced too. So this is actually known as F on L. The force per meter is same as mu naught I1 I2 over 4 pi r squared value too. The formula that you have to, so this is sometimes written as F is then equals to mu naught I1 I2 L over 4 pi r squared, like that. Okay, but because we have a mu naught and 4 pi always with a constant, in some textbook it's still using that F on L is equals to K times I1 I2 over 4 pi r squared, like that too. With the for K is same as given value. It's actually given 4 pi times, what's the value equals to? I've got the extra value. It's given on your page. 2 times 10 to the power minus 7. Yep. Oh, because we are talking about interaction. This means it's not a multiplying. It's a little more complicated. It's more about interaction. Okay, so it's not a mathematical terms. I'm just showing you that it's interaction between these two magnetic fields. Some of the magnetic field kind of, you can think about it here. If we create plus this to magnetic fields going opposite directions, it creates the greater size of the magnetic field. Does it make sense? Okay, so that's what we learned from previously. So in this case, you get the 2r value is given in here from the r, and the r is kind of combined. So it creates the greater 4 pi r square value, and we're going to consider about this actually coming in the kind of volumes of that too. But as I said, this is getting a little more complicated. The easiest way to approach the question is remember this, or remember this. But this, okay, we used to learn as this back into before the 2019. I learned that in this way. I learned that in but I learned that in university in this way too. Now from 2019 syllabus, we're not using the K value anymore. But some textbook or some school teacher probably use that. So this is why I'm introducing, telling you that, okay, if you see that, don't get afraid. This simply means from here, as we know, mu naught 4 pi squared is always B. 4 pi is always constant value, which is 2 times 10 to the power minus 7. Just take that as it. But you won't find the K value anymore in your formula sheet in that reason. Instead, you will see that mu naught will be given in your formula sheet. Okay, so this is the force formula you might need to use to figure out the forces between two conductors for your prac. No, you don't have to. When the formula is given, unless I don't think you need I don't see the need to derive that. It will be given formula 2. More likely for the pracs, you need to use that to get the relationship in terms of motor effect of the relation between two conductors. Okay, so that's how we use it. Okay, page 65. Could you highlight that, please? I'll tell you. I'll probably give you up to 10 to 20 sets of the trial papers. By the way, that set of trial papers you were not able to get it from. I know you guys can download some trial papers online nowadays. It's good. Use that. It's a good resource. But some school trial papers are pretty terrible. I must say that. Okay. What I'm trying to give you is I try not to give you anything from you can download from online because I buy it, I made it. So in many of the trial papers, you probably see this one question at least one time. We haven't had that in the HSC yet. I don't think we'll get the HSC questions, but in trials, what can they ask you is, hey, how do we get the standard unit, SI unit of the ampere, which is the unit for the current? And to get the current, we actually use the formula, this one, F1L equals to mu naught I1 I2 4 pi r squared. Okay, what the ampere was the one that found that found the current. So we now give it the name of the ampere to the unit of the currents too. What he did was he assumed that we have a length of 1 meter. We have a length of 1 meter. Okay, and then if the two currents, which is the same amount of current, produce the force amount of the 2 times 10 to the power minus 7 Newton, because he was able to produce the 2 times 10 to the minus 7 Newtons, that would be defined as the 1 ampere. So it's kind of reversed that too. He knew about the presence of the 2 times 10 to the power minus 7 because he knew about mu naught at 4 pi squared is always the constant value. R would be some constant value as well too. Okay, which means when we get to achieve that force of amount of the 2 times 10 to the power minus 7 Newton, that is the time that we started having the current of the 1 ampere. Does it make sense? Okay, and according to Newton's third law again too, when the same a certain amount of force is applied to the one current side, same amount of force in the opposite direction will be applied to. Now, I know it's hard to understand. Memorize it. I'll give you a shortcut. If you want a shortcut, yeah, this is a shortcut. Memorize it. If you get questions about, hey, how do we define the ampere, you get a full mark just explaining that. But if you can understand a little bit of that, and which will help you to memorize in this content, yeah, that's how we get the 1 ampere unit too. And later on, we're going to learn about how we get the unit of the 1 second in module 7. How do we know 1 second is 1 second? When do we start getting the 1 second exact? Okay, that's related to the speed of light. All right, shall we do a question related to that 2.6? Please, let's do it together. Determine the force per unit length acting between two current carrying conductors, both carrying the 10 amps of the current in the same direction, spaced 10 centimeters apart. So what we have to do, 10 centimeters apart, is giving a clue that the distance between two wires. Let's write it down. I1 is equals to I2, that is given as 10 amps. R, which is distance between two wires, given as 10 centimeters. Convert that into the unit of the meter, which is 0.1 meter. Mu naught is given. Let's write it again. 4 pi times 10 to the power minus 7 newtons per m squared. Okay, so bring it out. F on L, the formula is equals to mu naught I1 I2 over 4 pi r squared, like this. Remember that this is not talking about the force, it's the force per unit, force per meter, first of all, here. Substituting all the relevant values we have 4 pi times that 10 to the power minus 7. I'm just going to figure out whether it's a 4 pi or 2 pi. It's been a while. Sorry, guys. Okay, it's a 2 pi, of course. Yeah, had a feeling. My bad. It's 2 pi r, so it would be times that, 10 times 10, and 2 pi r squared. So what you see there is pi will be cancelled, and 2 cancel 2. So this is why the k is where the k comes out from, 10 to the power minus 7 2. Okay, then you to see, just using your calculator, you have to don't have to use that. So 2 times 10 to the power minus 7, that times 10 times 10, and divided by r squared, that was given as 0.1 meter square. You get 0.002. Units would be newtons per meter. Yeah, because we're following the unit of the force per length. Or the question asking you, what is your force per meter, force per length of that? Are we done? Are we done? There's a 1 mark question. If you just answer that like this, you get 0. Why? Direction. The question never asks you the magnitude, it asks you the force. And this is why I ask you to memorize that. Same direction they will attract, opposite direction they will repel. You don't need to think twice. Just memorize it. It's given. It's running in the same direction, means that they will attract to each attraction or attracted to each other. Just write it down. This is the key. This is the point. Like, and you will get a more complicated question using the direction as well too. For example, let me give you one question again. I will probably continue some of the questions later on too, but you get this type of question before, and there's actually what HSC question we had before here. Assume that we have a 1.0 amp for the I3, I2, I1 going into this direction. That's I1, it's going into 1.0 amps. And distance between here is 1.0 centimeters, and this is also be 1.0 centimeters. Now, question's asking you, what's the force on the I2, the current 2, and the current carrying conductor 2? I'm not going to go through every single answers, but you must think about it in here. Oh, I have I2, there's I1 and I2 in this situation here. Think about this situation there. They're running in the same direction, aren't they? Therefore, they will be attract to each other. So there will be some force from these two. But if you saw that, another wire on the top, yeah, this and this in running in opposite direction. So what does that mean? There will be some force from these two as well. So you need to find the net force value. A force from two same conductors, another force from that two. Okay, maybe these two will be like repelling each other too, and another force from these two, adding all the forces acting on each other. Okay, so this is how we make the question from the simple content, simple formula there, how the thing's getting more complicated. Similarly, you can have the 3 wires with a different distance too, running in the same distance, same direction, up, but down. Okay, I want very typical HSC question style in multiple choice. Ask you to find what if the force exerted onto I3 then. Okay, this is the type of question that we're going to go through again, and I will show you the some practical questions that are related to the current carrying wire or the motor effect. So please do not forget that. Current carrying wire or current carrying conductor in the B field will produce a motion. That's called the motor effect. Or saying that when there's I, there must be induced B. Okay, in 2 weeks later, I'm going to teach you something different. When there is B, there will be I then. That's known as the induction, the principle of the generator. Any questions up to here? So homework, please finish up the rest of the HSC question chapter 1. Okay, chapter 2 questions, I will give you some HSC question related to, and I would like you to do some try yourself questions here as well too. Start from question 10. So question 10 of try yourself, page 74, and the rest of try yourself questions up to question 16, please. So six questions, 10 to 16 in try yourself, as well as the HSC question. So you don't lose the understanding about the motor effect. Well, that's it.